Hello everyone. Continuing on the inverse of matrix, we are going to be doing part 2 of it. The things we have done earlier, we talked about what is a matrix, some matrix operations, transpose of a matrix, and in part 1 we talked about definition of invertible matrices, some properties, and a determinant of a 2x2 matrix and its relationship to that matrix. In this session, guys, we are going to be talking about an invertible matrix and how it is row equivalent to an identity matrix. We will see the powerful row reduction algorithm of being used here. And also if A is row equivalent to I, and then we will notice that when you apply this row reduction algorithm, the identity matrix after those row operations becomes the inverse of that matrix. And then we talk about what's an elementary matrix. Let's start with a little inverse of a matrix. We all know when we say when a matrix is invertible, that means there exists another matrix, and which is always we're going to talk about square matrices. So let me say it again, that a matrix A of size n is invertible if there is another matrix of size n, say C, such that A times C and C times A's identity. We call C to be the inverse, and we use the notation A inverse. We say when A is invertible, we write A inverse times A with A inverse's identity. Another name for an invertible matrix is a non-singular matrix. Let's talk about the determinants. When we talk of a determinant of a 2x2 matrix, it basically means if we have a 2x2, the quantity AD minus BC is called the determinant of that matrix. We write it as determinant of A equals A with two vertical bars on it, next to either side of it, equals AD minus BC. Very powerful theorem. If you have a matrix A and if AD minus BC is non-zero, we say A is invertible. The inverse of the matrix is given by 1 over AD minus BC times the matrix D minus B minus C and A. Notice this matrix is nothing but you are flipping the diagonal elements, and the other elements are just multiplied by minus 1. This theorem 4 is very helpful because if you want to know whether a matrix is invertible or not, you just simply figure out its determinant. And that is very useful because it saves a lot of computation for us. Let's do some more examples from the book. We start with this problem which says, suppose P is invertible, and we are given an equation where a matrix A equals a matrix P times B inverse, and then we have to solve for B in terms of A. Notice this equation which is given to us, by default we're going to assume that this matrix product is possible, or it is always going to be true, let's say this way. Okay, let's solve for B now. So we have A equals P, B, P inverse. Because P is invertible, that means P times P inverse equals P inverse times P is identity. So that's what we do is we multiply this equation with P on the P inverse on the left and P on the right. We do it on both sides of the equal sign. So we get this next equation. And then we look on the right hand side of this equal sign, we notice that P inverse P, we know the identity. And then when we gather that, we basically get identity multiplied to a matrix P, which basically is the matrix P. So that takes care of the right hand side of the equal sign. And the left hand side basically is giving us the answer that B equals P inverse times A times P. Remember guys that these are all matrices. Okay, another example from the section of this book. It says we have 3 n by n matrices, suppose they are A, B, and X, with A, X, and A minus X to be invertible. And also we are given that the relationship that A minus AX inverse equals X inverse P. We are asked why B is invertible and can we solve this equation 1 for x. Before we proceed, keep things in mind from Theorem 6 that if x and a minus ax are invertible, that means their inverses are also invertible, which in turn means that a minus ax inverse and x inverse are also both invertible. Okay, let's look at this equation 1 given to us. A minus ax inverse equals x inverse b. Now remember, we want to say why b is invertible. So what we'll try to do is get b on one side and see what happens on the other side of the equal sign. So we can get rid of this x inverse. Remember, x is inverse is invertible. We can multiply by x on both the sides of this equation. Then what we get is x times a minus ax inverse equals xx inverse times b. Remember, x is invertible. That means x times x inverse is identity. And identity with the matrix B gives us the matrix B itself. On the other hand, what do we notice is the left-hand side of this equal sign gives us x times a minus ax, the whole, this expression to inverse. Now, this B is a product of two invertible matrices because x is invertible and a minus ax inverse is also invertible. Again, by Theorem 6b, we see B is invertible because it's a product of two invertible matrices. Well, let's look at this, solving this equation 1 for x. Okay, let's look at that. Solve this x for x. That means we want x on its own. Now, from the equation 1, when we played, our little computational, we found b was equal to x times a minus ax inverse. Okay, we're going to start from there because we want to solve for x. Now we've already got x on one side, so we need to really work on this part and get it on one side, okay? Okay, now let's look at this one. What are we given, guys? We are given that x times a minus ax, the whole inverse, equals b. Now b is invertible. We have already proved that. That means b inverse is existing and it is also invertible. Okay. So what is b inverse? It means basically you're taking the inverse of the left-hand side. So when you take the inverse, remember this one, so if you have C, D inverse, the inverse is given by D inverse, C inverse. Now my C, remember, is x and my a minus ax inverse is D. So what it happens is it becomes a minus ax inverse, the whole of that inverse, times x inverse. And so when you look at this part, notice it's an inverse of an inverse. That means it's the, the original matrix A minus AX. And then we have X inverse. Now we can, because remember the associative property, all of them are matrices, we can basically, and also not the associative, I'm sorry, it's the distributive laws. We can distribute X inverse into, inside these subtraction of two matrices. So we will have AX inverse minus AXX inverse. Now remember, X is invertible, that means this is identity, and we get A times I, which is an A, and then equals AX inverse. Notice, we have B inverse, this is B inverse, equals AX inverse minus A. Now we can add or subtract any matrices, so we add A on both the sides. I'm doing it on the, as if I'm adding A here, so I would like to have B inverse plus A. Doesn't matter if you put A first or B inverse. Remember, matrix addition is commutative. It does not matter how do we write that. So what we get? We get B inverse plus A is A. Now remember, A minus A will cancel out. We have AX inverse. Okay. Now, remember, A is invertible. So we can multiply both the whole equation by A inverse on the left-hand side. And when we do that, on the expression on this one is, remember, A inverse A times X inverse. Now A inverse A, guys, is an identity matrix, so you get X inverse. Notice over here, what is it? This is A inverse times B inverse plus A. Once again, I'm going to use this little trick because I'm having D inverse C inverse. I can write the left part of it and apply it on this part of the equation. So I can write this as B inverse plus A, the whole inverse. In other words, what I'm doing, B inverse, so now remember this is the second matrix, and I'm taking inverse of this matrix, and this A comes here, and then we have inverse. Okay, and that's what we have here. Okay, give me a second, guys. I think okay, let me just make it much more. So you say B inverse plus A inverse, this whole expression to the inverse times A times inverse, and that's what we have here, equals X inverse. Now notice this whole expression, I'm going to write it much more nicer. You have B inverse plus A, this is the whole inverse, A and this little inverse equals X inverse. Now remember, by quality of matrices, if you're looking at the inverses, the inside part is the same. And that's what we're looking, solve for X. So this comes here and the X comes here. And that's how we get the answer. So your final answer, X is nothing but B inverse plus A, the whole expression inverse times A. Okay, let's now start with elementary matrix. So what's an elementary matrix? An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. That's it. One single elementary row operation on an identity matrix. Okay, let's look at some elementary matrices. And we have three elementary matrices, E1, E2, E3, and a matrix A. So this elementary matrix, E1, now remember what's an identity matrix. Identity is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, if I'm talking of E1, what does it mean? If you notice, we are multiplying the first row by -4 and adding it to the third row. So that gives me E1, which is basically -4 times R1 added to R3. The change is made it an R3. What's E2? E2 basically is flipping the identity matrices R1 and R2. That's what is happening. That's flip of these two. What's E3 doing? E3 is basically multiplying the last row by a 5. Now what we like to do is we like to see, these are elementary row operations, and we would like to see what this elementary row operation does when it is multiplied to A on the, and these elementary row operations are kept on the elementary matrices, are kept on the left hand side, or that's the first matrix and the product, and the matrix A is always the second matrix. Okay, so let's see what happens when you multiply E1 with A, E2 with A, and E3 with A. What do we notice? So when you multiply E1 with A, I've kept these two matrices, you will notice you actually get this. This is basically what we are doing is if you move from this matrix A here, we are applying the elementary row operation -4 times R1 plus R3 going to R3. And that's exactly what is done. Which basically it means is when we apply these elementary row elementary row operations on any matrix, what we are literally doing is we're doing an elementary matrix of the same operation applied on the identity matrix and multiplying it to the matrix A. So that's what basically it is. Similarly, let's look at E2 and E3. What do they do to that matrix? Remember, E2 is a matrix which is basically interchanging row R1 and N2. So when you multiply it with the matrix A, it also basically interchanges row 1 and row 2 of the matrix A. Similarly, when you multiply E3 with the matrix A, what you see is that the original matrix A is having a last row multiplied by a 5. So this is a very important fact about some elementary matrices. I'm going to just put them in some observations here. It says that if an elementary row operation is performed on any m by n matrix, the resulting matrix can be seen as an elementary matrix times that matrix A. That's what it says. Another thing, every elementary matrix is invertible. And the inverse of that matrix is that elementary matrix of the same type, which will transform the matrix, elementary matrix E into I. So in other words, if I am interchanging two rows of an elementary matrix, and I again re-interchange those rows, I get back the matrix itself, the original matrix. Okay, let's do an example to explain what I'm saying here. It says T2 is a row operation which adds -2 times row 1 to row 2. So we would like to find that elementary matrix which does that T2 operation. So remember, when we talk of an elementary matrix, what basically I'm saying is that row operation, only one single row operation applied on the identity matrix. So when we do this one on the identity matrix, this is the matrix, new matrix, we get E5. And we said that every elementary matrix is invertible. So what would be the inverse of this elementary matrix? Remember, it will be doing the same kind of row operations, but little change in what values. So what we do is that inverse of this matrix is basically now we'll be multiplying the second row of the identity matrix by 2 and adding it to the we are going to multiply the second 2 times the first row to the second row. Remember, the original matrix you're multiplying by -2. The inverse of that elementary matrix would now multiply by 2. But you're going to do the same operation. You're doing a multiplication of a row to another row and making the changes in that row. That's what you're doing. And notice when you multiply E5 with E5 inverse, you will always get the identity matrix, just to make sure that you're doing the right thing. Okay, so we have talked about what is the definition of inverse of a matrix. We've talked about this relationship with determinants. We also learned about elementary matrices. But we do not know how to find the inverse. Remember, we said that we can every invertible matrix is row equivalent to the identity matrix. And when we apply the row reduction algorithm, what happens is that the identity becomes the inverse. So now we are actually going to get that theorem out and then do an example. So theorem 7, a powerful theorem, which says if a matrix is invertible, if and only if A is row equivalent to the identity, and in this case, when you're having a sequence of row operations, it will reduce A to I identity, and the identity transforms into the inverse of that matrix. So in other words, we have AI put together, and then we apply these row operations. And if the matrix is invertible, then A will be transferred to the identity, and identity will be changed to the inverse of the matrix A. Okay, so this is another way of finding the matrix. Let's go ahead and do an example. So we would like to find the inverse of this 3 by 3 matrix. Remember, when you want to find the inverse, the idea is apply the row operations simultaneously, and we want to get this A into the form 1 0 0 0 1 0 0 0 1. That is the technique we want to do. So the first thing we do is, as we want to find the inverse, we're going to do it simultaneously, whatever operations we do on the A to the identity matrix. So what happens is, when the row reduction algorithm is applied on this A, it transforms A to I, and the I will be changed to the A inverse. So let's go ahead and do this row reduction algorithm. I'm just going to quickly go over it. We have done it many, many times now, and I've shown you all the operations I'm doing. Okay, the first operation, guys, I'm going to do is I am going to interchange row 1 and row 2 because I want the first row and the first column of the matrix A to become a 1. And that's the most simplest way to do. You interchange row 1s and row 2. And that's what this operation does, and we get this new matrix. And remember, I'm simultaneously making a change in the identity. Remember, this is A, this is A. Okay, so when we do that, let's go to the next set of changes. Now, what we're going to do is we need to get this, so we need to make this to be 0. So you multiply a -4 to R1, then add it to R3. You get this scenario. Similar, it's applied to the whole matrix over here. Please be careful. This is not the augment matrix. Be very, very careful. This is not the augment matrix. It is like it is using the theorem to find the inverse of the matrix. Okay. Keep that in mind. Okay, so we are over here, guys. Now we want to make, now remember, 1, 0, 0 is there. We want to have 0, 1, 0. We need a -3 to be 0. We do this operation. So that's where we go, and the operation is done, and we get the 0. Okay, notice I need to get a 1. So we have got 1, 0, 0, 0, 1, 0. I need to make the last column before the vertical line to be a 0, 0, 1. The first thing I need to make is 2 to be a 1. So we applied this 1/2 of R3 to R3. So we get this. And after that, we need to make this 2 values above the 1 on the third column to be 0s. Just do the row reduction algorithm. Wow, we get the A we started with to be identity. And the identity is now becoming the A inverse. Okay? So Theorem 7 has helped us a lot, and here we are. We have found the inverse of the given matrix by just row reduction algorithm to simultaneously to the matrix A and the identity together. And when we do it, and then later on, we can also check whether our answer is right. So we can do A with A inverse, because remember, A is invertible. It should always give the identity. Well, guys, now it's time for you to practice. Here, so we have section 2-2. These are the questions I want you to work on: 19, 21, 22, 24, 29 to 31. Thank you, guys. Oh, I see there's a mistake. This, guys, is section 2-2. Okay. Thank you.